Now it's recording. So what we're going to be talking about here is stereoisomers. And basically what I want you to consider what's going on is stereoisomers are a specific kind of comparison where we see differences in the 3D shape of the molecule. So we're talking about differences in the 3D shape of the molecule. Now, this is different than when we talked about constitutional isomers in class, because constitutional isomers are molecules where there is a change, right? That we move a methyl group from across, or we change the ring shape, or we do something with it. But stereoisomers have the same formula, and they have the same connectivity. So they have the same formula and the same connectivity. And what I want you to know is that keeping that idea about same formula, same connectivity in your mind is really going to help you with understanding what's going to happen later on. So before we even dive in, what I want to do is I just want to talk about, okay, where am I? As my reference says, is I just want to help you guys indicate, are we looking at the same molecule, different molecules, or, stereoisomers? So as you guys might have seen in class, this idea about wedging, here's a wedge bond, and here's a dash bond. And whenever you see a wedge bond, a filled in triangle, what I want you to know is that the substituent is facing you. And what do I mean by that? Well, is if we took a table and we had a molecule lying on the table like that, so maybe we're talking about butane. What's happening here is that if it's a wedge bond, the group is facing up and out of the table. So it's like it's leaping out of the page at you. So if you were staring at your piece of paper right now, imagine you're a group that is coming up like that. All right, so it's facing straight up. Versus when we talk about a dash bond, or sometimes called a hash bond, is the substituent is facing away from you. So again, what does that mean? It means that it's coming down through the page. So it's like now if the substituent is below the plane of the piece of paper. So with this in mind, we can start talking about, let's just practice identifying same structure. So we're trying to say, is it the same structure? Stereoisomer, or constitutional isomer. So let's just do some practice. Well, actually, no, I want to put it there. Ha ha ha. I don't know. I don't want to do a ton of these. I want to do. And then let's do one more. So for each pair, let's go through and let's talk about if each one is the same structure, a stereoisomer, or some sort of wait, you're doing this right. Yeah, cool. So for number one, remember that for stereoisomer, we're talking about same connectivity, right? Whereas constitutional isomer is different connectivity. So we can obviously see in this first pairing that here we have a 5-carbon chain versus a 7-carbon chain, right? And then those 6 and 7 carbons are now substituents. So we can say that obviously this is constitutional isomers, right? That same formula, different connectivity. Whereas for the one below, we can see once again that we have 1, 2, 3, 4 carbons. So same number of carbons. They both have a double bond, so they both have the same degrees of unsaturation. So we can assume that these are constitutional isomers as well. All right. So this should be pretty familiar. We did this on the last exam. You know, we talked about this. If you need more practice, there's tons of it in the Google Drive. So go take a look. For this green one here, what do we notice? Well, we have the same carbons, the same number of carbons, and we on both carbons kind of 1 and 2, if we wanted to say that this was 1 and that's 2, we have a chlorine. So before what we were talking about right now, we could say, oh yeah, perfect, done, boom, same structure, right? Because they have the same connectivity, same structure. However, what we're going to be doing is we're going to be talking about this idea about rotating and flipping molecules and stuff like that. So what I want you to imagine is that we're going to draw a line going through this molecule. So we're essentially taking it, and if this was my molecule, I'm putting a nice pin that I'm going to be able to rotate the molecule on like this, rotating it back and forth, back and forth. And what I want you to notice is that what's going to happen is that as I rotate it, whatever on this half, once I flip it upside down, will rotate onto that half. So what's going to happen is that when I take something and I flip it upside down, and this is a property of flipping, is that whatever you find on one half of a mirror, you'll find on the other half of the mirror. And we can see that this carbon maps onto that carbon, that carbon, that carbon, that carbon, that carbon, chlorine onto chlorine. So at least we can say that there's a mirror going on. And what we notice is that when I flip something, something maps onto something else. So we can say that this chlorine will match that chlorine. And when I flip something, whatever was facing away from me on the dash bond will now flip to face me on a wedge bond, and vice versa. Whatever was originally on a wedge bond will flip to give me whatever on a dash bond. And, you know, these kind of visual representations of what's going on is really important. I like using my phone because the phone is square and we can kind of talk about it. But, you know, so what we see going on here is two things. First, that when I flip this chlorine flips onto that chlorine. So again, same connectivity. But what I notice is that when I flip, wedge turns into dash, wedge turns into dash, which gives me the exact other structure that I'm talking about. Did I have to manipulate the molecule in terms of like picking off a bond, sticking it into a different place? No. All I did was a simple flip. So if all we're doing is flipping, rotating, kind of manipulating it in our mind, and nothing, and we're able to get the other structure, then this is what we call the same structure. So these two molecules here are the same. And once again, make sure this makes sense for yourself, is that we're saying something is the same because we're not changing the nature of the molecule. I'm not picking bonds off and placing them somewhere else. I'm not changing the wedging and dashing in terms of like forcing this now to be hashed. All I'm doing is flipping it. And the process of flipping creates the mirror and creates the opposite effect, which is why we went from wedge to dash. But I didn't necessarily have to change the molecule. The molecule already existed in that capacity. So whenever you see a same structure, what I want you to think to yourself is, does A, everything map? Everything map in the flip? And B, does the stereochemistry or does the wedging and dashing match? So it's kind of the two steps to what we consider, are we doing everything that we're doing correctly? And later on, I'm going to give you a kind of flow chart for how we're going to be able to determine these things a little bit more in a second. But let's take a look at this other example real quick. Once again, we see that we have the 6-carbon ring, and that's the same. But what do you notice? Well, now carbon 1 is a carbon, and carbon 2 is a chlorine. But maybe I can call this carbon 1 and that carbon 2. So maybe this is what it is. So if that's the fact, I need to somehow flip carbon 2 so that way it's in this position here. So once again, I'm going to do that sort of idea about, I'm going to flip it along this axis. And when I do that, the chlorine should match up over to there, just like how we talked about before, that when you flip over to this position, we should see a change, which I should have labeled this correctly. This should be 2 and 1. My bad. Ha ha ha. So when I flip, I change the position. So if this was 3 and 4, this should now be 3 and 4 up here. So we're changing the position of everything. And then likewise, we said that we have to make sure that the wedging and dashing. So I expect this dash to turn into a wedge, right? And I expect this wedge to turn into a dash. And what do I see? Well, I see that the chlorine moved to the right location, but I see that my wedging and dashing has not. Once again, I see my carbon has moved to the right location, but again, the wedging and dashing has failed. And so this is what a stereoisomer is. A stereoisomer is one where when everything is mapping, everything maps in the flip, all the carbons have the same connectivity, carbon 2 still has the chlorine, carbon 1 still has the methyl group, but the 3D nature of the molecule fails. And so that's a stereoisomer. Same connectivity, different 3D representation. Kind of sort of with me so far? Does this make sense? If you have questions, let me know. There's a whole bunch of practice that I will write down later, but I want to get to the rest of what we're talking about. But I will give that to you so you guys can practice, and then we can go over it later and everything. So what I want to go into is this idea about enantiomers versus diastereomers. And this is probably the section on the exam where upperclassmen would groan because they hate enantiomers versus diastereomers. But what I'm going to tell you is that it becomes easier with practice. And the reason why people generally shy away from these sort of things is because they just don't like practice. So what I'm going to tell you is that get your hands on as much practice as you can, because you're going to want to be able to practice these things, especially if you felt the test one was a little bit hard. This is the exam that people are like, oosh, like, wow, this was tough. So we want you to be able to understand what's going on. So let's say that we have two molecules. I'm going to draw it just slightly differently, just so that way. Good enough. So cyclohexane looks terrible though. And let's say that we're comparing these two molecules. So we're talking about, we're putting a dash bond there, maybe a wedge bond there. Oop, actually, let's put a dash bond here. And maybe a wedge bond here. And the molecule that we're comparing it against looks like this. And the question becomes, are these the same molecules or are they different molecules? Or are they the same, constitutional, or stereo? But what kind of stereoisomer are they? Are they the enantiomer or the diastereomer? Well, right off the bat, what we can see here is that we know that they're not constitutional isomers because we see they have the same bonding. Cyclohexane ring, 3 carbons on carbons 1, 2, and 3. We can see what's going on. But what I want you to consider is that if we take this molecule, and once again, if we rotate it, put a line right through all of this stuff here. And what I want you to imagine is that we're taking it and we're rotating it this way. So again, we're taking it, spinning it like this. What we see is that we get something like this. So again, in our imagination, we can say that if this is carbons 1, 2, and 3, then this should be 3, 2, and 1. So carbon 2 doesn't really move. And what we see going on is that we get dash, dash, dash chlorine, right? Because carbon 3 is changing. Carbon 2 is going to change as well. Now it'll be a wedge. And carbon 1 is going to change. And so what we see in our mirror is what we're checking to see if, oh, maybe we can mirror it to get this compound, is that we see that we don't have the same compound, right? Here, this is wedge, wedge, dash, and now we have dash, wedge, wedge. Well, what if we took it and we rotated it like this? What if we kind of spun it kind of like a top on my finger or something like that? Well, even spinning it on a top like this, we still wouldn't get the same positions, all right? We still wouldn't get this carbon 1, this position to somehow get into that, right? It would never rotate that way because if this rotates kind of this way, then this is going to rotate to there. And so what's going to end up happening is that now I'm going to have carbons, if I tried rotating it, 1, 2, and 3 in that regard. So they'll never line up. So if you have two molecules that are what are called non-superimposable, this, wow, I'm not doing good with the spelling today. Non-superimposable. This is what brings up the definition of a stereoisomer. So stereoisomer in general is going to be talking about non-superimposable. all right? So we're talking about molecules that do not overlap, that do not match up. So that's the question that you're asking yourself to really identify stereoisomer, non-superimposable. To identify enantiomer versus diastereomer, we're going to ask ourselves another question. For enantiomers, we're going to be talking about mirror images. Versus for diastereomers, we're talking about non-mirror images. So what do I mean by mirror images? Well, what I mean is that if we put a mirror up right here, you know, if I put it right in between our two molecules, boop, boop, they're looking at ourselves in the mirror, everything kind of like that. On the other side of the mirror of this hash, of this dash, should be a wedge. And so what a mirror, essentially what I want you to think about is that our dashes changed into wedges, our wedges turned into dashes, and our dashes turned into wedges. And if we look at what's going on, yeah, our hash turned into a wedge, our hash turned into a wedge, and our wedge turned into a dash. Perfect. So the first check mark that we had to determine was, are they non-superimposable? Yes. If they are, we can move on to the second step, which is determining enantiomer versus diastereomer. And what we see is that all of our dashes turned into wedges and all of our wedges turned into dashes. So if this is true, these are enantiomers. So the definition that I'm going to give you for enantiomer, or a cheat sheet that I'm going to give you for enantiomer, is this. For an enantiomer, and this is how I kind of go about it as well, because if you try to go about it the way in the book or someone might teach you, it takes way too much time. So this is my quick way of doing it, and I'm going to show you the official way of doing it later. For enantiomers, all of your dashes turned into wedges. All of your dashes turned into, well, read the symbology. I can't think right now. All your wedges turned into dashes. All your dashes turned into wedges. All right. Is this always true? No. And so this quick and easy, this quick and dirty way of figuring out enantiomer, and we'll later learn the quick and dirty for diastereomer, isn't an end-all be-all. All right. It's a way for you to help frame your mind ahead of time so that way you can determine if what you're doing is the correct pathway. All right. So the quick and dirty way is saying all of my stereochemistry changed. Does that make sense so far? Cool. If we go into another pairing, so we're going to copy that same first molecule just because, I don't know, maybe I liked him. Maybe he was a good guy. So here's my cyclohexane. I drew a much better one this time. So that same guy that was there before, so I believe that he had a dash there, a dash here, and a wedge there. And now what I want you to do is I want you to compare them against, you know, a wedge there, maybe a dash here, and maybe a wedge there. We'll try that one. Let's see this one. Well, first steps first, we have to determine, is it a constitutional isomer? And what we can see is that no, they are not constitutional isomers because, again, 6-carbon ring, 6-carbon ring, carbons 1, 2, and 3 all have the same number of chlorines on it, so not constitutional isomers. Well, then what we do is we check to see, are they non-superimposable? What we do, take our mirror, And again, what we see going on is that here's carbon 3, 2, 1. They've mapped the other side of the mirror that we're talking about. And what we see is that we expect that this wedge should turn into a dash, that this dash on carbon 2 should now be a wedge, and that this dash should now be a wedge as well, right? Same molecule that we were talking about before. And when we compare this mirror, the mirror, to the other molecule, and if they do not line up, then these are non-superimposable. And so the fact that they're non-superimposable, which, why can I not spell this today? The fact that they're non-superimposable means that we're starting down this path of determining if they are stereoisomers and what kind of stereoisomers they are. So it's this comparison that tells us non-superimposable. And then in order to determine enantiomer versus diastereomer, we need to go back to our original comparison. And what we can say is that, well, here we have a dash that turned into a wedge. So that's a check mark. But then we have a dash that failed to turn into a wedge. And again, we have a wedge that failed to turn it into a dash. And so the definition that I'm going to give you for enantiomer versus diastereomer, let me just copy this so that way I have it all on one page. Oh, I should have checked to make sure that was going to work. That's all right. The definition that I'm going to give you for a diastereomer, and the one that I use and the one that I think of to, quick and dirty, is that for a diastereomer, let me write it over here. For a diastereomer, at least one bond fails to change. So at least one bond does not turn into a wedge, or at least one bond does not turn into the dash that we were expecting. So if you have more than one bond, perfect. If you only have one bond, that's totally fine. And what this tells us is that these are non-mirrors. That diastereomers are non-mirrors. And just to compare this against what we were talking about for enantiomers, is that we were saying that all of our bonds change. All of them change to what we were expecting. All right, so notice the difference. Enantiomers mirrors, and in mirrors, everything has to change, right? Like if you go look at yourself in the mirror in the bathroom, everything about you has changed. Versus if you looked into a mirror and let's say that your eyes didn't change over, or your freckle that's on the left side of your face stays on the left side of your face, then you would have somehow a diasteric mirror, and in which case you kind of broke physics. So congratulations, sell that mirror to NASA. So what I want you to know is that this quick and dirty way works a good amount of time, but there are chances where it doesn't. But for all intents and purposes right now, we can keep working with it. How does this, is this making sense so far? Have you guys talked about this in class yet? No? Okay, good, because I wanted to make sure that I did this ahead of time. So let's say that we took this molecule, this one over here. I like this one because it has this nice like shape going on. I also drew it really nice, which is primarily why I copied it. Here's a really shitty one. And I don't know, let's say that now we have dash, 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 dash chlorine, wedge chlorine, and dash, 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 dash chlorine. Well, again, these are not constitutional isomers, same connectivity. And what we notice is that they do have a difference in their shapes, right? So if we wanted to do the mirror analysis, which I generally recommend, what we notice, and I know I'm writing things down really fast because I'm able to copy and paste, but I will give you guys a second to copy in. If you guys actually want to just stop writing for right now, and then I'll give you like a 2 minutes to kind of copy everything down. Because sometimes students try to write everything and they miss it. So I'd rather you guys just see it first. So, or you can rewatch the session, whatever's easier for you. What we notice is that we expect in the mirror that our dash turns into a wedge. Our wedge turns into a dash turns into a wedge, and our wedge turns into a dash. And what do you notice? What we notice is that these molecules here are the same, right? They're the exact same molecule. So are these non-superimposable? No, these are superimposable. So if you are superimposable and you have the same connectivity, which was, step 0 that we did before, same connectivity, you are the same molecule. All right? If you can mirror it, if you can rotate it, if you can kind of flip it on its head and spin it around, and you get the same bonding, the same molecule, then you are the same structure. All right? And so it's the same way that if this comparison is the same, then we can say that these are the same as well. Okay? So if the mirror match up, then the original 2 comparisons also match up. How do we feel about that? Good? Cool. I will give you guys a second to kind of copy that down if you need it. All right. My ears just kind of popped right now. That was weird. Um, let's talk about the next part about stereochemistry and this idea about enantiomers and diastereomers a little bit more. You might have seen this in your textbook somewhere, or you might have seen it talked about in class probably later on this week, is this idea of chirality. And what I want to tell you is that if you look at your hands right now and you kind of hold them up to your face and you examine them, what you can notice is that they're mirror images of each other, right? And because of that, they're mirror images, but each hand is unique, right? On my left hand, I have the thumb facing the left. On the right hand, I have my thumb facing the right. But if I tried to put my right hand so the thumbs were facing in the same direction, what I noticed is that now I have the top of my right hand facing upwards, right? So they can't ever be the same. And if they were, you were probably born a little bit differently. So chirality is this idea that you have a molecule or an object that has points on it where they're unique. And that uniqueness is what creates stereoisomers. So what I want to tell you is that um, for a molecule to be an enantiomer, it must have a chirality center. And what you might be saying is a chirality center, it's a point of difference. So, my hands, my thumbs are the point of difference. You could talk about, thousands of different things. I could take two pencils and I could say, oh, this one's has a, different color. That would be a point of difference. So things like that make it so that way you cannot superimpose. So a chirality center, by definition, um, allows a molecule to be non-superimposable. Right? However, there are a couple of exceptions to this, okay? We'll talk about what a chirality center specifically is, but before we go into that, what I want to tell you is ways that you cannot be chiral, okay? You cannot be chiral if you have symmetry. If you are symmetrical, you are unable to be chiral, okay? And if you are not chiral, you cannot be an enantiomer or a diastereomer. So with that in mind, what we can do is we can, instead of looking at every single point on a steroid or something like that and trying to determine the chirality centers, what we can do is we can check to see if there's symmetry, because symmetry is really easy to see and it's something that you can look at and determine instead of having to do something more complicated later. So there are three kinds of symmetry. There's center of symmetry, there is the plane of symmetry, and there is the axis of symmetry. In each one of these together, if you have one, you cannot be a chiral molecule and you cannot be a stereoisomer. So with that in mind, let's just kind of go through and talk about what is going on, all right? What I want you to consider, so first is we're going to talk about the centers of symmetry. Center of symmetry. What I want you to do is I want you to imagine that you are standing in the middle of this molecule here. all right? You're standing right smack dab right in the middle right there. And what I want you to notice is that the center of symmetry, what it's telling you is that when you're standing in the center of the molecule, you're creating a plane of symmetry. So you can't see center of symmetry in this 2D function. You have to almost draw the molecule in a 2D function. So doing that, what I can see is, if this is carbon 1, 2, 3, 4, 1, 2, 3, 4, what I notice is that the BR is above, is it? Sorry, not a BR. This is supposed to be a chlorine. Ha ha ha. My bad. What I notice is that this chlorine on carbon 3 is above the plane of symmetry. Put this in red. Right? How do I know that? Because it's on that wedge bond. And what I noticed about the chlorine on carbon 1, it's below the molecule. In the same way that I can kind of fill in the hydrogen that's left over here, and I can fill in the hydrogen that's left over here. Because remember that we don't write hydrogens, right? All hydrogens can be hidden when they're on carbons. So every molecule can have a dash and a wedge bond per carbon. So what we can say going on is that there's a little hidden hydrogen right here. Oh, that's kind of hard to see. There's a little hidden hydrogen right there. And what we can say going on as well is that there's a little hidden hydrogen right here, right? So every carbon can have a wedge and a dash on it. Because if something is above, then we need something to take the place of below, right? Because we need to have 4 bonds on a carbon. And here are the 4 bonds of the carbon. And what we see going on is that if we're standing right in the center of the molecule here, what we notice is that we can have a plane of symmetry between these 2 chlorines. Okay? And once again, we can see that there's a plane of symmetry between this hydrogen and that hydrogen as well, right? So this plane of symmetry cancels out the ability for the molecule to be chiral. So this molecule cannot have an enantiomer, okay? Does this make sense? Well, this is all well and good, right? Great. I drew a molecule in 3D, but what if A, I'm really bad at being an artist, or B, I can't visualize this in my head? Well, what I want you to imagine is that we're placing a invisible line going through this molecule, right? And what we're saying is, does this chlorine map onto that chlorine in terms of when we flip it, does it change the stereochemistry? So the chlorine maps onto a chlorine. That's the first check. Boom. And does our dash turn into our wedge? Yes, it does. Okay. Same thing for our hydrogen. Our hydrogen maps onto our hydrogen. And does our wedge turn into our dash? Yes, it does. Okay. So this is the center of symmetry. You're standing in the middle of the molecule and you're noticing a change. This will look kind of similar to what's going on with the plane of symmetry. And in all intents and purposes, I generally think of them as the same, but you might be asked a question about the center of symmetry, so I wanted to tell you about it specifically. Cool. With that in mind, we can go on to the plane of symmetry. All right. Do I need room? I might need room. Number 2, the plane of symmetry. The plane of symmetry is probably the easiest kind of symmetry to see, okay? And unlike the center of symmetry, where we expect wedging to map onto dashing to show that kind of three-dimensional change going on, plane of symmetry is like you're taking a piece of paper and you're folding it, all right? So this is almost a two-dimensional way of comparing a molecule. So what I want you to know is that in this case, instead of mapping group to group, what we're doing is we are cutting the molecule in half, just like we're doing origami, all right? So if we took this molecule and, you know, we can fill in some information going on here, that there would be some hydrogens here. Again, what we can see is that we have, we know we have some hydrogens here. We'll talk about those in a second. And what we see going on is that if I took and I just folded it right down the middle, right, then that would be symmetrical. Simple, right? Just like we did in second grade or third grade, I think was Massachusetts Board of Education. So the what's important to know going on here is that this is a plane of symmetry, okay? Wedge chlorine maps onto chlorine. So chlorine maps onto chlorine, wedge maps onto wedge, okay? That's a plane of symmetry. Here we have H maps onto H and dash maps onto dash. Boom. Notice again that this is different than the center of symmetry, right? Where we would need to be in the center of the molecule if we wanted to check the center of symmetry. We'd need to be in the center, and we draw a line like this. And what we see is that there is no center of symmetry because there is no line that goes from one substituent to the other one, okay? And so what we can say is that this molecule is in fact symmetrical, and it does not have a chirality center. So it is not chiral, and it will not have an enantiomer. Here's the issue. If we fill in these hydrogens here, we know that each bond must have a dash and a wedge, right? And there's two hidden hydrogens. But wait, wedge doesn't map onto dash. So did I just lie to you? Did I just tell you that this molecule is symmetrical when it's not? No, because remember, molecules are symmetric. If they're 3D shapes, they are not 2D shapes. So just to show you what's going on in kind of a 3D fashion, here we have the chlorine sticking above the plane of symmetry. Here we have the hydrogen sticking below the plane of symmetry. And what I want you to notice is that we have the hydrogen sticking up and the hydrogen sticking below. So what we're essentially doing is we're taking this molecule and we're slicing it kind of through its, through kind of like we're taking it and slicing it right in half, right? And what we see, or what we see going on, oop, I drew the wrong line of symmetry. Ha ha ha, my bad. What we're doing is we're kind of taking it, we're slicing it almost like we're slicing it like this, right? Slicing it going right back. And what we see is that the chlorine does in fact map onto the chlorine, the hydrogen does map onto the hydrogen, and that this half of the hydrogen molecule maps onto that half of the hydrogen molecule, and this half of the hydrogen molecule maps onto that half. Because remember that molecules are, or atoms are really balls. So that's what we're describing going on here, okay? And so what I want you to be aware of is that when you cut through a bond like this, when you cut through a single atom, we're really mapping the left half of an atom to the right half of the atom. And so this is why this molecule is still symmetrical, even though if we do the bond wedge analysis, it looks like it shouldn't be. Does that make sense? Okay. The rule of thumb I always go through is that if I'm cutting through a carbon, like if I'm going right through it, then I don't count that one in terms of the in terms of the plane of symmetry analysis, because that's just going to screw it up, right? So that's the quick and dirty way of kind of looking at it. How do we feel about this? Good with me so far? Hopefully I'm doing a good job, better job than I did last year. Last year was a bit tough. I didn't have as good of a lesson plan. The last one is the rotational plane, or the rotational, or the axis of symmetry, okay? And basically what this is saying is that if you have a molecule and you are able to rotate it into itself, then you have symmetry. All right? So if I have this, borane right here going on, what I know is that this thing kind of looks like a triangle, right? And that I can, if I spun this thing kind of like a top, almost like I'm taking it and spinning it like this, what I can see is that this hydrogen will rotate into that hydrogen, this one will rotate over there, that one will rotate over there. So just like a pizza pie, it's rotating around, right? And so this is a rotational axis of symmetry, or an axis of symmetry. And what we see is that this molecule is not chiral, okay? Where did we see this before? I'll tell you. It was with this molecule. Oop, I drew it the wrong way. It was with this molecule that we had done earlier. Right? And what we did is we rotated it in our minds, and we saw is that chlorine, that we were doing the comparison. We rotated it in our mind, and what we saw is that in the rotation, we ended up getting the comparison. So we ended up seeing the same molecule. So this is why it's the same molecule, is that not only does it have a rotational symmetry, because we rotated it and we got, the same molecule, but it also has a plane of symmetry going right down this middle part, right? Because what we can see is that chlorine maps onto chlorine. Wedge maps onto wedge. So this is why that earlier comparison that we had going on was, in fact, a same structure answer, is because it had a rotational axis symmetry and it had a plane of symmetry. How do we feel about this? Good? Kind of? Should we do some practice? Yeah. Let's do some practice, shall we? So once again, just to fill these in, we have the center of symmetry, which sometimes you'll see labeled as I. We also have the plane of symmetry, which sometimes you'll see written as, I think that's sigma. And you have the axis of symmetry, which you'll see written as N. Just so that way, if you're ever reading this and you see like all these weird words, what's going on. So let's say that we have, I don't know, let's say our first one is that guy. And all we're doing here is we're trying to determine how much symmetry we see. So the number of symmetry going on. Oops, that's just the same thing. And we are not comparing molecules here. We are simply just practicing number of symmetry, even though I drew these things in the same color, and I really should not have. Let's do, I don't know. And before you tell me off that there's no way that this is a real molecule, it is. I think it's called prismane. And last one will be this guy right there. All right. Let's talk about these, shall we? All right. Let's start with this one up here. So for this guy, this fluorinated ethyne, what we can see going on is that it has a center of symmetry, right? If we stood in the middle of this molecule and we drew a line from one substituent to the other one, what we'd see is that we get a match. So there is a center of symmetry there, right? Quite clearly, and probably the thing that you saw most of all was that it has a center of symmetry, right? Or a plane of symmetry, right? The question is, well, how many? And what I want to tell you is that there is an infinite number of symmetries. The reason is this thing actually looks like it's just a tube. And so if you take a look at any tube that you have around you, and if you look at it head on, what you can see is it's just a circle, right? And how many plane of symmetries are in a circle? Infinite amount. So there is an infinite amount of plane of symmetries in this one. And then finally, how many axis of symmetries? Well, I believe there would be, I believe there is, well, we can rotate this thing onto that thing, like we're spinning it like a top. We can also rotate it almost like we're kind of like rolling a joint, I guess you could say. That's the term you find it. So in this case, I believe, oh God, I think there's 3 in here. Will you have to be able to figure out how many of each symmetry is in there? No. Okay. Most professors don't really care. They care more that you're able to identify it. All right. I just think it's helpful. So we won't go with the numbers anymore. Cool. For this guy over here, what do we think? Well, if we check the center of symmetry, what we see going on is that we expect there to be a methyl group on a dash. And what we see is that there is not. So there is no center of symmetry. We can't find a plane of symmetry, right? Because I can't cut it, top to bottom, because then I would expect a methyl group over here. And I would expect then a double bond here. So there's no plane of symmetry, not left to right either. So there's no plane of symmetry. And again, even if I took it and the one that people miss all the time is if I slice it like this, if I slice it through, I should expect to see a dash here with a methyl group, but I don't. So that's why there's no, I think that's axis 9 planar symmetry, but I can't remember. So there's no planar symmetry. And finally, I can't rotate this in any way, so there's no rotational symmetry. So there's no symmetry at all. So is this molecule chiral? Yes, it is. This molecule is in fact chiral. Same thing here. I can see that there is a plane of symmetry there. It would have, so is there a center of symmetry? Well, if I draw a line from this guy to that guy, what I see is that they don't match up, so there might be no center of symmetry, but there definitely is a plane of symmetry. And I can rotate this thing like a top and rotate it that way, and I'll get the same thing. So there is a rotational axis. This guy over here, what I see is that there is a center of symmetry, so I have that. There is not a plane of symmetry, because even if I did it this way, chlorine doesn't map onto hydrogen. Even if I did it this way, chlorine does not match up onto hydrogen. So this is no plane of symmetry, I believe. Is there a plane of symmetry? Oh, there would be. If you take this thing and you put a table on it, put it through the table, and you cut it right in half, what we see is that the top half of the chlorine matches onto the bottom half of the chlorine. Ooh, oh God, that's a nightmare. So there is a plane of symmetry here. And I believe there is a rotational axis, because if I rotate this around, I would actually map it onto there. So there is for that one. Again, if you find one thing, you know it's non-chiral or achiral, right? So is it important to find all of them? No, but it's important to be able to talk about all of them. Same thing here. Here's a plane of symmetry. There's, I don't believe, a center of symmetry, but there is a couple of plane of symmetries, actually. And so I don't believe there is a center, but it does have a plane and it does have rotation. Because if I take it and I flip it like a pancake, what I'd see is that this maps onto that. So what I'm doing is I'm kind of doing that. And then boom. This guy over here, put this one down to talk about the center of symmetry again. If I draw a line from here, I expect to see a chlorine on a dash. I do not, so there is no center of symmetry. I do notice a plane of symmetry, though. And there is rotational symmetry. And then finally, for prismane, what we see going on is there's a whole bunch of planes of symmetry going on. We have, this one that cuts right through that one. We have another one that cuts through this guy in the front, another one that cuts through this guy in the back. So there is planes of symmetry. I don't believe there is a center of symmetry, and this thing has a whole bunch of rotational axes. So this is more just a visualization practice. So if this was fairly easy for you to get at least one plane of symmetry if they existed, great, you're doing great. The reason why I do so much with the symmetry is because sometimes if this was difficult for you, you need to put a whole lot more work into stereoisomers than other people are going to do. Just how your brain works, different stuff like that. But if this was difficult, then you are going to struggle if you don't practice more. Last note about symmetry, and then I promise we will for the love of God, stop talking about it. When you see things like benzene rings, okay, what I want you to do is I want you to turn these into the circle benzene ring that I told you earlier you're not allowed to do. Well, when you're drawing them for an answer or something like that, you are not allowed to do them. But the reason is because if you did it this way, we'd only see 3 planes of symmetry when there's actually a whole bunch more. There's some here going through. So I believe there is like a whole bunch, okay? So there's way more planes of symmetry showing the circle than it does showing the double bonds. Why this is important is because if, let's say for instance, you had a molecule that was written like this, all right? What you'd say is, okay, I can identify the plane of symmetry here, but you'd miss the one that's here, okay? Because you'd say, oh, but I expect to see a double bond there. But what I want you to know is that these are actually supposed to be delocalized. And so because they are delocalized, we can see, in fact, that there is another plane of symmetry there. Okay, so that is the only time that you are allowed to write the circles if you must write the circles. All right. So we did all this work to determine which structures are symmetrical. But that's not really answering our question, because the question was, we need to determine where the chiral centers are, okay? Where the points on the molecules are that make them chiral, okay? So how am I doing on time? What time do we end? 5:30? Okay, we're gonna have just enough time. For chirality centers. So first of all, if you have a chirality center, and you are asymmetrical, you are a chiral molecule. Okay. But what we talked about this symmetry business all before, but now we have to talk about this idea about chirality center. All right. A chirality center, to be a chirality center, you need to be an sp3 hybridized carbon. Okay. So not sp2, not sp. You must be an sp3 hybridized carbon with 4 unique groups attached. And why does it need to be sp3? Is because to be sp3 means you have 4 bonds. Okay, go back to that idea about steric number that we talked about before. So if we look at this molecule, all right, what we can see is that this carbon here is an sp3 hybridized carbon, and does it have 4 unique groups? Well, it has a CH3 group, it has an H, it has this 1, 2, ethyl portion, and it has this 1, 2, 3, 4 butyl portion. So all 4 of these groups attached to this carbon are unique, so this carbon is chiral. And then we check to make sure that it's not symmetrical, and what we see is that this molecule is in fact asymmetrical. So this molecule is chiral. It has a chirality center, and it's asymmetrical, so it is a chiral molecule. All right. So with that in mind, let's take a look at another example of a chiral molecule where we're not told explicitly what the wedging and dashing is, because I don't necessarily need to tell you the wedging and dashing to make it a chiral carbon. So let me just label some carbons for us, so that way we can all talk about the same thing. And the question is, circle the carbons that are chiral. All right. Well, with that in mind, first of all, I know I can skip all of these carbons that do not have substituents on them, right? Because I know all of them have 2 hydrogens. And to be chiral, you need to have 4 unique groups, and I have 2 of the same, so automatically I can get rid of those from my head. Same thing with terminal carbons. Terminal carbons have 3 hydrogens, and so are not going to be chiral either. So the best thing to do is to look at where I see substituents. All right. So let's start with purple over here. Is purple chiral? Well, if we look, we can see that we have the chlorine. We can see that we have the chain going towards C6, right? But then what we see is we have a hydrogen and a hydrogen. So this carbon is achiral. All right. Go into the yellow carbon. And this isn't even sp3. This is sp2 hybridized. So it can't even be considered to be chiral because it is not the correct kind of hybridization. Go on to the blue one. And what we notice is that we have NH2, an amine. We have towards carbon 2. We have towards carbon 3. And we have that hidden hydrogen, right? 4 unique groups, chiral. But wait, there's no wedging and dashing. You don't need wedging and dashing. It's helpful because it kind of clues you in on a place to go, but you don't need it in order to determine chirality. All right? So just because a carbon is not labeled wedge or dash does not mean that it cannot be chiral. One last example to talk about. Let's compare these 2 molecules. Well, for this girl, it's because it's pink. For this molecule over here, what we notice is that we have a potential chiral center. So what we can say is we have chlorine, and a hydrogen. But if we call this 1, 2, 3, 4, 5, 6, what we notice is that carbons 2, 3, and 4 are the same as carbons 6, 5, and 4. So both of these pathways are exactly the same. If your pathways are exactly the same, it's probably because you have a plane of symmetry going on. All right. So we do not have 4 unique groups. And the reason why we do not have 4 unique groups is because of symmetry. So again, remember that the first check is checking for symmetry. Well, I hear you say, what if we had something like a methyl group here? You know, what if I had a methyl group here? Well, then carbons 1, 2, and 3 are different than carbons 1, 6, 5, right? Because there is no plane of symmetry anymore. And what we see going on is that what am I trying to say? That the pathway going 1, 2 to 3 is different than 1, 6, and 5. So we have on this molecule, what we can say is that we have a chlorine, a hydrogen. Group 3 is towards C2, and group 4 is towards C6. So this carbon here is chiral. Likewise, we can look at this carbon and we could say we have a methyl group, we have a hydrogen, we have towards C3, which is different since towards C1. And so what we can say is this carbon is chiral. And because we have 2 chiral centers and no symmetry, we have a chiral molecule overall. Finally, let's take a look at this molecule. Well, we see that we have 2 potential chiral centers. And what we see going on is that, well, let's check for symmetry, right? Well, if I try to say there's a plane of symmetry, I expect wedge to map onto wedge. But that's not true because I have wedge map onto dash. There's no plane of symmetry here. And so when we do the bond analysis, what we see is towards the, 1, 2, 3, 4, 5, 6, towards C2 is different towards C6. So this molecule is chiral, or this carbon is chiral, sorry. For the green one, we can say that we have a chlorine, a hydrogen, towards C3, which is different than towards C1. So this carbon is also chiral. All right. So because we have a chiral center and no plane of symmetry, this molecule is chiral overall. How do we feel about this? Good? Okay. This is probably the second hardest part of this entire chapter, is identifying chiral centers. Not specifically at MCP, but at Northeastern and BU and Hawaii, you all are going to have to do this, and you're going to have to be able to count how many chiral carbons there are. I don't believe MCP has to do that. If you look in the Google Drive, there's tons of practice on how to do it. Go look up cholesterol and try to figure out how many chiral centers in there, or amoxicillin or heroin. There's tons. Different stuff like that. All right. Here is an issue. Well, it's not so much an issue. We just talked about it. That if, so just to recap what we talked about, that just because you have a chirality center does not necessarily make you a chiral molecule, that you have to look at the symmetry as well. And if you're symmetrical, then you are golden, and we can go forward. We're going into CAP. Maybe I can kind of sort of get this done. don't know if I necessarily want to talk about this today. I think what we are going to do is we are going to finish up early because I didn't expect us to kind of get through everything as quickly as we did. So when we come back on Wednesday, we're going to talk about the con-angled Prelog system of nomenclature for determining absolute chirality or absolute configuration, I guess I should say. So we'll do that on Wednesday just because that deserves its own time. Is there any questions, anything like that I can say? How you doing, Olivia? Are you still with us? I believe you are. Yeah. All right. This will go up later tonight. If you have questions, reach out. Go look in the BU class notes for first semester. There are tons of practice in there. If you go and look at the stereoisomers, if you want to read through his stuff is great. Feel free. If you have any questions, please reach out. Go find some practice. They're everywhere. Oh, I don't know if I showed this to you guys. But if you have a, can you guys see the Google? Okay. Let's say that if you wanted to look up like finding chirality centers practice, okay? If you type this in, you're going to get like a lot of different things, and maybe this isn't what you want. So what you can do is you can type in file type :PDF, and this will only bring up PDFs of practice problems. All right. So this is the thing that people are always like, do you have more practice of this? It's like, no, just go look it up. Okay. Because you can find it everywhere. Okay. You just need to know how to look for it. Right. And honestly, if you can find the, what's it called? If you can find the practice, usually you can find the answers. Sometimes if you put dash answers at the end, right before it says PDF, sometimes it will bring it up. But it depends. Like if I tried it here, dash. Oh, I think underscore answers. Yeah, it doesn't work. So, play it by ear, or send it over to me and I'll look it over for you. The other thing too is that if you're ever like, oh my God, I don't know how to do this topic, like, I don't know, what's on your biochem exam tomorrow? Amino acid, trying to think of like anything that you guys are learning last year. Amino acid, biochemistry, and I change it to PPT for PowerPoint. What you can do is you can get only PowerPoints of what's going on. So like that just downloaded for me. And so what you can do is you can get PowerPoints of different things and you can take a look at different stuff. Is that helpful? Yeah, yeah. So use this kind of Google techniques to your advantage. I just found something as well that I just wanted to show you guys. This thing, which is the reaction map. So this shows how all the different reactions from, if you started at one molecule to how to get to every other kind of molecule. That I found this, and by God, it is intense. So MCP won't necessarily know all of this, but definitely my other schools will. So expect by the end of the second semester for me to whip this thing out and for you to understand a good deal of it. All right. That is where we're going to stop for today. If you have questions, let me know. And good luck on your biochem exam tomorrow as well. You guys have biochem, right?
I don't, at least. But thank you, though.
Oh, you guys are second years.
Yes.
Or the third years. I tutor way too much. Cool. All right. I will see you. Have a good day.
Thank you, you too.